Okay, the first law is, no. The first law is law of dominance, okay? Now another law is the law of segregation, and then the other law is of independent assortment. Okay, I will, what to do? Okay, I'll just give you an introduction of this law of segregation. Now we have seen this already in proof. We have seen the proof of the law of segregation in gamete formation. Now in the cell, we started with the zygote, or in the cell, we started with 2n, no? 2n because in this chromosome, in this cell, this, let's say, is a chromosome pair. This gene A aligns with this gene A. This gene B aligns with this gene B. Then this gene C aligns with this gene C. Okay, we know that they are in pairs, but what happens, and this is 2n, okay, ठीक है, yes, this is in pairs, yeah, I know I am in a pair, right, but what happens in meiosis? So, we will get 4 cells, and each of this cell will get half only, no? Okay, meiosis because it gives you 4n, no? N. Now we know that here there's only A, there's only B, and there's only C. Okay, let me just, here, let's say in this gamete, only A, only B, and only C. And in this other gamete, only A, only B, and only C. Okay, so we see that they segregated, didn't they? First they were in pairs, no, AA. But in meiosis, this one has only A, this one has only A. So we have seen, for sure, we have seen clearly during meiosis that they do segregate. So what he theorized, he doesn't know what is happening inside our, inside our ovum, right? He doesn't know what's happening inside the spermatogenesis. He had no idea. He just gave the theory, but it is proved now that they do segregate. No, these pairs of alleles, they do segregate. So there has been proof, right? So let's look at the other law, that is the law of independent assortment, also known as the inheritance law, okay? These show that alleles of different genes, they will assort independently of one another during gamete formation. Means A will assort differently to B, okay, and differently to C. Doesn't mean that A and B will go together, or A, B, C goes together, or A, B, or A, C. No, it doesn't depend on each other. A has its own place to go to, B has its own place to go to, C has its own place to go to. Okay, fine, maybe they are in the same chromosome, only God knows, but there are so many genes, there are thousands and 10,000s of genes, just think. So in this long chromosome, A might be here, B might be there, C might be there, no? And when they are pulled apart, A might get with ZXY gene, B might get with A square, B cube, you know, you understand. So they are assorting independently of one another. Just because A, B and C were together doesn't mean they will go together, okay. So even though he mixed one trait, that is one white flower and purple flower, he always got the same ratio, 3:1, okay, between the dominant and the recessive. So it means that regardless of whether you took a recessive male, whether you took a female, we did was purple, right, that time. So whether you took a female who was white or the male who is purple, it makes no difference because they will segregate and assort independently. So he concluded that different traits, okay, whether it's a size, a shape, a color, a height, they will assort independently, okay. Even if you mix a yellow seed and a purple flower, and then white flower with a purple seed, green seed, no matter in what generation, in what combination he makes, he still get 3:1 ratio. Okay, how do I explain this? Okay, let's say, here he took purple flower, yellow seed, and then green seed and white flower. The first generation he makes like that. Then he makes another way, he makes P, W, Y, G. Then another generation he makes W, WP, G, Y. Okay. Whatever way he mixed, he will always get 3:1 ratio. No matter what combination he does, he still get 3:1 ratio. And again, when he does the F2 generation, means when he sells that 3:1 ratio plant, he keep getting 3:1 ratio, 9:3:1 ratio. So he concluded that because I have mixed whatever probability I could think of, whatever combination I did, I still get the same result. So I must conclude that these factors, they must behave alone. Whether I am sending them in group 1 or sending them in group B to do practical or sending them in group C to do practical, they are still doing the practical well because they are working alone. You get it? So he realized that they must be assorting independently of each other. Okay, so I think there's nothing more clear than I can make than that. So we know this, that during meiosis 1, we are seeing those independent assortment. Okay, now in this day and age, after the electron microscope and all, we could see how the genes actually behave. So we actually see in practical what he thought, what he just imagined, that independent assortment. We are seeing that when they pair, pairing during meiosis 1, you will learn with Miss. During the metaphase of meiosis 1, they get a gamete where they pair between the maternal and the paternal chromosomes, right? And something that happens was the chromosome crossover. So this you will do during when you do with meiosis. So you will see firsthand how that independent assortment happened, okay, how the pairing occurred, how the exchange of genes occurred, how the crossing over occurred. So that crossing over, that gene knows that I have to go, no matter what random group Sir Mendel kept me, or respected Mendel Sir kept me, I will do my work. I will have to cross over and perform. Okay. So when Mendel published his work, it was mostly ignored because it was something so new. They had never heard about factors, okay. So they were not completely unknown. There were many biologists who referred to his work. And now it has been rediscovered by the new biologists, especially Correns, De Vries. All these are the rediscovery work. Okay, so this is not important to know. Now let's look at the laws in detail. Okay, so he formulated 3 laws and they are named after him. So these are Mendel's laws of heredity. First is law of dominance and recessiveness, then your law of segregation, and then the law of independent assortment.